So today it's our pleasure to welcome Professor Hilke Schlichting for today's informal astro seminar. So after completing her PhD at Caltech with RAM, she went on to postdocs at CETA and as a Hubble Fellow at UCLA, where she is now a professor in, I think it's Earth, Planetary and Space Sciences, and an associate dean for language. And an expert in many topics, dynamics, but today we'll hear about planet formation and connecting the atmospheres of planets to their interiors and all the fun processes there. My personal favorite, magna-oceans. So please take it away.
Thank you very much. Welcome everyone. Yes, so I'm really interested in planet formation from all angles, from dynamics, from formation history, from structure. And I guess more recently I've gotten interested in some of the chemistry as well. So it's been a steep learning curve. And since it's an informal seminar, we're not that many, so feel free to ask questions as we go along. I certainly don't have an agenda to get through every single slide, so I'd rather for you to learn something interesting than me showing you n number of slides in the next sort of 45 minutes. And the other thing is, I don't know how many of you actually regularly think about exoplanets, so please, make sure you ask if I use some jargon or don't explain things well, because probably I've been thinking about them for too long by now. So with that, this is sort of the state of the art, right? So I think for me personally, and I think for many in the field, the biggest surprise in sort of exoplanets has been, amongst many, but really it's this new population of planets that were discovered mostly from the Kepler spacecraft originally, right? These planets that exist inside typically the orbit of Mercury, so inside 100-day orbit periods. And in size, they are in between anything we have in the solar system, right? So between sort of 1 Earth radii and 4 Earth radii. So like Uranus and Neptune are roughly 4 Earth radii. So in the solar system, we don't have a planet, right? Inside the orbit of Mercury, you would know about this for many reasons. Actually, somebody challenged me the other day and I'm like, dynamics, we can rule out. I'm like, oh, maybe in the past. I'm like, no, you can't just easily stick in a big planet there. It will make havoc of the rest. So we don't have one of those planets like this in the solar system. And so it's an very interesting population from a planet formation point of view, right? So because we focused a lot of our understanding of planet formation on the solar system for a long time. And then the other interesting thing about this population is that it seemed to consist of sort of two distinct subpopulations. And we call these small planets now, the larger ones here, sub-Neptunes, and the smaller ones here, super-Earths. And they really do seem to divide in the space, both in sort of orbital period and planet size, if you plot it. As well, if you do the same, sort of plot the same population as a function of planet size and stellar mass, you also see these two populations. So that's very intriguing. My group and a couple of other groups have led a lot of work trying to see if these populations are connected or distinct. And the general conclusion is that these super-Earths most likely formed as part of the sub-Neptune population and then lost the hydrogen-helium envelopes that these planets have and became super-Earth over time through hydrodynamic escape. And we can talk a little bit more about this later. But so it looks like most of these actually are connected sort of from a formation pathway. And then how do we know any of this, right? So in terms of their composition, we typically only get a radius, a planet radius, and an orbital period and stellar mass for these objects, right? We don't actually get a density. So we don't truly know what's on the inside, so there's a degeneracy. But there are a couple of interesting things. So for some, we do have planet mass measurements. You do get about density. It's still a general problem, of course, because you can have more than 1 or 2 compositions in your planet. However, especially for the sub-Neptunes, many of them are so large in radius that you basically can't explain them as just a mixture of water, iron, or rock. So you do need to have a couple of percent of hydrogen and helium on top of whatever is inside to explain their size. So that's like an important point. Yes?
Out of curiosity, what's the excluded region in the central plot?
The excluded region.
Black trend.
Oh, here?
Yeah.
Yeah, this is here. We actually don't have enough statistics, enough detections to do reliable statistics. That's why it's excluded. Yeah. So And also to your question, right? So the dots here are the actual detected planets, and you see there's many more closer in because the chance of a planet transiting or seeing a transit, right, increases. As
So that's bias corrected.
exactly, and these shaded, these colorful things are the bias corrected populations. But then eventually you just don't have enough data points to make this reasonable, and they were so good here to just be honest about it and just cut it out. So there are a couple of planets further out that have been detected through the transit method, but not many, and so you can't do good statistics with them. Yes. Yeah, great question. Other questions?
Can you remind us how the planet masses are measured?
Oh, the planet masses, traditionally they came from the radial velocity method, right? So you see the star move around the common center of mass with the planet, but most of the ones for Kepler are actually measured dynamically from transit timing variations. So most of the smaller planets, actually these guys, are multiple planet systems. And so we can measure the transit time so well that we can see them, transit earlier and later, and then infer the masses this way. It's been super cool. Like one of the great clever things that you can do with dynamics. Yeah, otherwise we wouldn't have masses for for many of the Kepler planets. Yeah, because also you get them almost for free, right? It's already in the Kepler data. You don't need to go and get telescope time. So we use Keck typically to get the planet masses of the smaller planets, but it's very expensive. It's a big effort. Yeah. Other questions? Okay. So this is sort of where we are with this. But because of James Webb, we are able to take things a little further. And so for the first time, we can well measure the atmosphere of these sub-Neptunes. And actually, I'm going to focus on these sub-Neptunes for the first half of the talk. So what we can do for the first time for several of them is to measure what's in their atmospheres. And so this is the transmission spectrum of one of those, so TI-270D. So you know it's in a multiple planet system because it has a D label. So there's also like a B and C companion, planetary companion. And this one is about 5 Earth masses. So it's right in the middle of the sub-Neptune region. It's a little bit bigger than 2 Earth radii. And it has about a hydrogen mass fraction of about 2%, roughly. And so we can now also detect what's going on in the envelope. And here is sort of this is the data, right? The points. And then we have basically a compilation of the different atmospheric species that could explain the data. So here, what the authors inferred is that what you can pull out is sort of water, CO2, and CH4, so methane, from the spectrum. What is interesting is that the mean molecular weight of the atmosphere is consistent with like 5 roughly. So it's not just hydrogen, it's these other species are like abundant enough to contribute significantly to the mean molecular weight. And this also then corresponds to what has been termed now in atmospheric metal mass fractions. You guys will be happy with this terminology, right? Metals, anything other than hydrogen, helium. So the planetary or the exoplanet people are sort of going with this. Anything other than hydrogen, helium makes up roughly 50%, maybe 60% of this envelope.
And the mean molecular weight comes from the scale height of the atmosphere.
Exactly, that's absolutely right. So how would we know that, right? The scale height basically tells you how large these features are. And so this is how you get a handle on the mean molecular weight. Yeah, very good. So then the question though is, what does it actually tell us about the planet? Because the mass of the atmosphere is about 2%, maybe 4%, if you do this actually better and self-consistently of the planet's mass. That's like a tiny amount of the overall planet. Most of the mass of the planet is inside, most likely in a mixture of rocky silicates and iron, maybe with some water. So does this tell us anything about what's going on inside? Or can we rule out or probe that some of this is going on inside? Or is this all we ever know? And it's quite different, right, from the typical Jupiter mass planets or Jupiter and Saturn in the solar system. They're mostly gas. And so it makes perfect sense to think that they accreted from the primordial disk and that the atmospheric abundances to zero order be similar to the disk, and then you enhance it somewhat by accreting additional material. But for these planets, sort of the accretion from the disk is just like a sprinkling on the top. They form pretty massive interiors. And so the question that I have, and I think that sort of we dedicated a lot of time in a couple of years on it, is like, so does this tell us anything about the underlying planet? Or will it just be like, we'll say, well, this planet clearly has some carbon and water. We don't know how much because we're only probing like the really thin upper layer, but it has some. And this is where we have to leave things.
Okay, what dominates the error on the mean molecular weight? Is it the depth of these absorption features, or is it the mass, the surface gravity? What dominates the error?
Great question. I actually don't know for sure. I think it's the features, although I need to double check what the true error is on this, because you have many features, so I feel like you should be able to pull this out better. So I don't know, we can check. I don't know from the top of my head. Yes.
So
Yeah.
I'm actually surprised that if you have 60% metal mass fraction, the molecular weight is so low.
Ah, that's a fun thing for us to think about. Yeah. So the reason is because hydrogen is so much lighter than anything else, right? So metal mass fraction is weighing things according to their mass. The mean molecular weight, you're counting things according to number, right? And so this is exactly why you can get a case where by mass, right, this one, you're actually dominated by things other than hydrogen, but by number, the hydrogen molecules still win out.
There must
Or
be
like
some
it's comparable.
consistency relation between the
Yes, right? Yeah, so and you can calculate one from the other. This is actually an interesting thing that is true for some of the sub-Neptunes, that the atmospheres, this one is actually comparable, right? So you double the mean molecular weight. So you can have cases where by mass you're dominated by things other than hydrogen, but by number you're still dominated by hydrogen, and where these two become comparable. Here they are actually roughly comparable, but this is why it's so counterintuitive. Yeah, another fun things about these planets. Okay, so to try to answer this question, what did we do? We did the simplest possible thing we could come up with, and we basically, started to think about what the structure looks like. So traditionally, when we think about planets, and I think it was the right thing to do because it was all we needed, is like we would model them sort of as these onion shells, right? You have a layer of atmosphere, you have a layer of mantle, silicates, whatever, and then maybe you have a discrete core. Like this is still how we model the Earth. And it works well for Earth because we're a cold planet and they are pretty distinct, right? We're standing on the surface. We can really treat our atmosphere separately from the interior. And we even have pretty discrete in and outer cores. But when we look at like a sub-Neptune, for example, and if you follow the atmosphere, if you do a self-consistent thermal structure as a function of radius, what you find is that, so you have the upper atmosphere. When you sort of reach the point at which you should connect to the surface or the magma ocean, you are at temperatures of several thousands of Kelvin. In this case, it's like 6,000 Kelvin. And if you then go deeper in the interior, you're probably at temperatures way over 10,000 Kelvin. So these planets are really, really hot. And this is actually after it's been aged and thermally evolved for a gigayear. So today, when we look at these sub-Neptunes, they are still crazily hot on the inside. The magma is all molten, strongly convecting, and everything is actually very dynamic. And it shouldn't be so surprising, because if you would be able to cut open and look into Uranus and Neptune today, right, you would find the same. Even Uranus and Neptune today are thousands of Kelvin on the inside. It's just we think of them as ice giants, so it doesn't seem the natural thing for us to associate with them. And the pressures that you have of the base of the envelope are, this is maybe less surprising, are like a couple of gigapascal or more. So then the question is, right, if you just have hydrogen sitting on top of a magma ocean, what happens? So clearly it's not correct to assume nothing happens, because hydrogen is a very reactive gas, as I think we all know. And so we asked them the question, what would be the implications of having a hydrogen-rich envelope interacting with a magma ocean and an iron-rich metal or metal core? So what would you get for the composition, the structure, the interiors, and the evolution of these planets? And then ultimately, right, we want to turn this around and say, what does the composition really reveal about in the atmosphere, reveal about its interior or the formation history? So can we really probe this? And can we rule out some formation pathways? And so then to do this, we basically constructed like a global chemical equilibrium model. So you let the atmosphere, the interior, and the metal core interact chemically, following these sort of 7 chemical species and with 25 different phase components. And so because it's a global chemical equilibrium, it doesn't actually matter which specific reactions you wrote down, as long as you make sure they're independent, right? You find the same solution. And so you can then just solve it to find what the state of your planet is, right? So it does tell you the global chemical equilibrium state of the envelope, a hydrogen dominant envelope interacting with a magma ocean and a metal interior. And so I will, in the rest of my talk, use various results from this and the implications, starting with the atmosphere, but then we'll also talk about what happens to the interior, right? What happens to the magma ocean? It will basically take in a lot of hydrogen and other species, and also the metal core. Yeah.
Do you know that these are the reactions that are happening?
So they're not, I do not know which reactions are happening. I don't need to know. The key is, because it's a global chemical equilibrium, you just need to make sure that you have completely independent reactions, like an orthogonal set. And then you span the whole reaction space, and you could pick out a different reaction network and then create the same solution, as long as you make sure that your reaction network also spans the whole parameter space and is independent. That's the beauty of chemical equilibrium models, right? There's just, you actually, in theory, don't need to write down any specific reaction, because you just overall minimizing the Gibbs free energy. If you have a kinetic network, it's different, but if there's a global chemical equilibrium, you don't need your specific reaction, right? You can use, basically construct any other reaction as a combination, linear combination of the reactions you've written down.
This requires you to assume the manifold, for example, is well mixed.
Yes, absolutely, right? So all of this, exactly. All of this assumes the mantle is well mixed and the atmosphere is well mixed. And then the one thing that we do is we let the metal participate in the global chemical equilibrium, where you, for example, didn't yet have core formation. Or let the core remove the metal from the mantle and just say, oh, somehow you already formed the core, and therefore the mixing isn't good enough to transport everything down to the core. Yeah, this is a huge assumption, and I know for sure it's not right in detail. It will not be correct for eternity. It was just like the very first thing to try. Yes. Yeah, very good point. And I will talk a little bit about how this breaks down in the atmosphere relatively quickly, but it's still sort of a useful initial condition for the base of the atmosphere to then see what you can see further out. Yeah.
How do you choose these 7 chemical species? Why exactly these 7?
These 7, because they were the most abundant.
This is like from these observations of the slides.
No, most abundant just in the universe, right? Hydrogen, carbon, they're not listed in order, but like in the most reactors. We left out helium because helium doesn't react. It's like and this was also the reason why you left off nitrogen, although people are extremely unhappy about this because we have a lot of nitrogen in our atmosphere. But we started to include more elements, but basically they're the most dominant planet forming elements. Right, so like, you know, what we stand on, most of the Earth is like MgSiO3 or 4. So that's, you can form in here, iron core, and then, yeah, carbon and oxygen. So it's just because they're the most abundant. Yeah, if you had focused on things that you can test well observationally, we definitely would have included sulfur. So that's another one that we're currently working on including, just because you can probe it well. It's very volatile, has an absorption feature. Any other questions? Yeah.
How did you choose the molecules? Like there could be more molecules than these, right? There could be Fe3O4, for example.
So again, it's It's just a global chemical equilibrium model. It doesn't in detail tell you exactly how the different molecules speciate. Yes, so, and you will see, I'll give you some examples for the atmosphere where you can then evolve into different species. Although if temperatures are very hot, you tend to get the simpler versions of most things. Yeah. Okay. It's actually a really fun numerical problem to solve because it has loads of minima and you need to find the global minimum. But that's another, if somebody's really interested in computational in computational solutions to some of these. So I'm going to give you a couple of example results. So this is now just for the envelope. So it's the hydrogen dominated atmosphere interacting with the magma ocean. So they ask the question, what does the atmosphere actually looks like just sitting above the magma ocean? And the typical thing we find is, and you can see two different temperatures, right? One that's 4,000 Kelvin and 5,000 Kelvin right at the interface. And you can see that the typical species you form, other than the hydrogen you already had, is CO, CO2, methane, and water. So one very robust result is that hydrogen interacting with sort of is entity or is composition like magma ocean produces loads and loads of water. So all these planets, if you find a couple of % of water, you can easily produce this just with the hydrogen interacting with the rock. So just detecting water doesn't mean you have to have formed outside the ice line or you need to have delivered the water. You can just make it in-house. And I chose these specific cases because this was for a planet mass very similar to TUI 270d. So you can, this one here will give you a range of mean molecular masses, sort of spanning that of what we inferred for TUI 270d. And you get a big range of metal mass fractions from like 40% or so, or 30% to 80%. So on like, you know, on the very low level, you can say, oh, so maybe this is consistent with TUI 270d. But you should be skeptical, right? Because this is just basically composition at the base of the envelope, just above the magma ocean. So what we observe is all the way up here, right? Sort of at the top of the envelope. So, and we know, although I think in the convective region, you can make arguments that things should be pretty well maxed. As the atmosphere transitions to become radiative, right, you need to be more careful trying to compare the same thing. So this then led Matt Nixon, who we've been collaborating with, to sort of improve on this. So basically, he took the chemical equilibrium results to give initial condition for the base of the atmosphere. And then basically what you do is you can calculate the self-consistently, basically, chemical equilibrium as you go up in the atmosphere, right? As the pressure goes down and temperature goes down, and then also account for rainout and condensation. And then this, of course, will back react on the temperature and pressure profile, right? Because you're removing mass as you go up. But then if you iterate between the two, you can find a self-consistent solution. And once you've found that, you then also have to allow for chemical mixing, especially above. So from across the radioactive boundary and above in the radiative region, as well as photochemistry, right? Because the photons from the star will also then modify what you see observationally from the planet. So doing all that, this is like the solution, basically. You can see basically the different abundances. This was the condition at the base, and the different abundances as a height in the atmosphere, right? This is pressure, so the very top is there. And you can definitely see things condensing out. But one thing that sort of I thought was quite encouraging is that the most abundant species, hydrogen, water, methane, and CO or CO2, they deviate somewhat, but the bulks are not more or less preserved as you actually go from the deep interior to the top. And then, of course, the really nice thing he did is he actually created a transmission spectrum from that. And so now these are the data points. And then this is basically his solution. He did worry about nitrogen a lot, so this is why there are two curves. But it basically shows that it doesn't make, including it or removing it doesn't make a difference in this case. So I would say, to zero order, the sort of a chemical equilibrium between a magma ocean and the envelope does give you a pretty good fit of this transmission spectrum. So I think, unfortunately, it's a little bit too early to claim that there's evidence that there has to be a magma ocean in TOI 270D because we haven't yet ruled out any other possibilities, right? But it's definitely consistent. And so I think I think this will be a way forward for us to really probe the interiors of these planets, because we can do self-consistently now, make predictions of what should be on the inside and then compare it with observations. And that's where we can confirm or rule out these various options. And so we are at the very beginning of this. I think the field is just starting to get to terms with that. But I think it's a way forward that we will learn something new scientifically about these systems.
What are the free parameters that go into this essentially?
In the spectrum?
Yeah.
Well, I think this is normalized at some level, right? Because you don't independently know the radius of the planet. So you flat field the spectrum. But I'm not sure there's other, because here they're not fitting. This is just the data. They're not fitting, fitting a spectrum.
For the synthetic spectrum.
Yes, I think again, I still think you normalize to some sort of radius, because to get a true independent radius, you need to also self-consistently solve for the interior structure, like for what's below the atmosphere, right? Because it comes from the center of the planet, and that's not handled to the level it's needed. Because I'm going to talk a little bit about now how it's also the equilibrium chemistry will modify the interior structure, and that's not accounted when this is normalized. So basically, one free parameter, in my opinion, is exactly why you draw this line. Right, other than that, you just, what the spectral features you expect for the molecules, and the chemistry told you what should be there. So I don't think there's any free parameters there.
But the temperature and pressure
And that's all self-consistently, right? So I don't think there's free parameters there. Because you also match, right, the observed temperature and the distance from the whole star, and you include the photochemistry you would expect from that whole star, and you have the spectral type and things like that. Yeah, that's why you went through it. This was a lot of work, a lot of extra work.
I might misunderstood a bit, but you say that whatever we observe, like the composition of the atmosphere, is from the outer shell. But how do we know? I can consider it in any line of sight which goes close to the surface of the star.
So this is for the planet, right? This is a transmission
so
spectrum
for
of.
the surface of the planet, yeah.
So this is, right, modeled for observing a planet like this, right? It's a transmission, so it's the stellar light transmitted through the envelope like this.
Most of the composition goes from the inner part. Is there
No, because you only unfortunately can typically transmit light through in the upper sort of radiative region of the planet. So it's not, unfortunately, it's not the inner part. I wish it would be the inner part. My life would be so much easier. Unfortunately, it's like the very upper, do I have a plot of this? Typically what they can probe is here. Millibar regions, which is well above the radiative convective boundary in most cases. Yeah. Yeah, if they could probe inside of the radiative convective boundary, I don't think we would need to do any of that. And then photochemistry wouldn't matter either. But sadly, typically we can only probe sort of in the very upper atmosphere. Yeah.
why does adding nitrogen make no difference? Is it because nitrogen is very inert?
Yeah, I think chemically it doesn't make a difference because nitrogen is very inert. That's why we hadn't included it. But I think they were concerned about pressure contributions from nitrogen, right? It's very inert. From a chemical point of view, it doesn't matter because of that. But you can then say, well, but it does matter from a for modifying the pressure and temperature profile, right? Because it's still there. And it can also contribute, of course, to the mean molecular weight. But I think the conclusion after all this, including it, was that actually it doesn't matter for the transmission spectrum in this case. I think going forward, it's easy to include if you just, because we initially only thought about the chemistry, it's not important for that. But I think if you want to do the self-consistent modeling, it's worthwhile to include, just like sulfur. It's just, the problem just gets more complicated very quickly. So you have to be a little bit careful where to start. Yes?
Yeah, so just to kind of get my understanding straight on this as well, the individual abundances or the inventory doesn't really matter because that's just being sourced from the mantle, or there's essentially this equilibrium isn't limited. There's no bottleneck in any of these reactions with one species being like the limiting ingredient, if you will.
It could be, right? So what is the ingredient, right? The ingredient is a magma ocean, and you know the abundances of this magma ocean. So you have this much silicate, you have this much magnesium, you have, you know, a certain number or moles of these various species, and you have a certain number of hydrogen atoms, right? So or a certain number of iron atoms.
So I just mean as in, would that not be, each of these be a free parameter then that would affect this? If there was like a limiting species in this global equilibrium, some sort of bottleneck, that could completely change.
Yeah, so I don't think the transmission spectrum is a good probe in actually abundances, because the features that you see, are, you know, as long as you see the line, you don't get a bigger feature by doubling the amount. I think if you do it in emission, you can try to constrain abundances. But I think here the abundances are mostly inferred observationally by modeling these together. So by finding a self-consistent, by having these present, but then finding a self-consistent solution between these various species and their features. Yeah.
Makes sense.
Yeah. Yeah, there's a lot of, and people do it in two different ways, right? The people call these like free chemistry models. That means they just they look for all the species. They don't account for the fact that, oh, if you have a lot of, I don't know, methane, you shouldn't have a lot of CO2 at the same time. I'm just making up an example. I'm not sure it's true. They just allow everything to be there and just see what features they see. And then there are some that include sort of an equilibrium chemistry and say, well, we need to like balance things out. But people still do both for most planets. And just see if you get consistent results, or how to see how dependent their results are on these assumptions. Yeah, I think we're gonna like see a lot of improvement on some of this analysis, I'm hoping, and going forward. Yeah, but it's like sort of the beginning, I think, of people trying to wrap their head around these things. Yeah. Okay, so that's one example. So hopefully in the future we can probe the sort of what most of these planets are made from, right? The bottom 95% from the atmospheres. I think there's hope. But it's possible. The conclusion could have been, we just can't. You can put in whatever you want and you just never can probe it. It's a very, actually, I thought this was probably what you find out this way. So I think, but I think it's good news. And I think you can also probe, for example, if the metal is participating in the chemistry or not. So whether the iron is sort of maybe already differentiated, or at least the transport isn't good enough to have basically reactions with the entire mantle. One other really interesting thing is, which we can test observation in a different way, and this is slightly easier for me at least to wrap my head around, this is the fact that you get a lot of silicate vapor right above. I didn't include it just before because it condenses out, and it is typically not visible in the upper atmosphere, although maybe for some very hot planets. But in general, just above the magma oceans, you know, at 5,000 Kelvin or whatever, you get crazy amounts of silicate vapor, because silicate will want to be in vapor form, not in solid form. And so you get sort of a little bit like a water cycle, but for silicate vapor on these planets. So very close to the surface, it's so hot on the silicate from the magma ocean will evaporate. Then, because as you move up in the atmosphere, right, it cools and eventually it'll condense and then it'll rain out. But the one thing that is very different for these planets in terms of in terms of the analogy with the water cycle is that silicate, of course, has a much higher mean molecular weight than the background gas, hydrogen. Whereas on Earth, right, water is lighter than our background gas. So for Earth, this doesn't happen, but for these planets, as the silicate vapor is so heavy, or it can be so heavy. And here's like an example. You can see this is the partial pressure of these different species. This is the inner convective region here. That's the outer radiative region of the planet. You can see that in terms of abundance, you get water, SiO, and hydrogen as the dominant species. So you get so much silicate vapor that basically you can inhibit convection. Although you have a huge temperature gradient, the silicate vapor makes the gas basically so heavy that the temperature gradient can't overcome this, and you can inhibit convection. Here you have plotted the mean molecular weight and see at the base, it's like almost 10. And then it drops as you go up in height, because the silicate vapor starts raining out. This one here, we only have silicate vapor and hydrogen and water. And so then you can ask, well, why is that interesting? I mean, it's cute, but why is it interesting? It's interesting because it fundamentally changes the way that the planets would evolve thermally. Why is that? So this is our idea. We have a silicate dominated core, then we have this convection inhibited region just above. Then eventually, once the silicate vapor all has rained out, you're convective again, and then you're radiative in the very upper layers. If you cut them open, right, the temperature profile now, instead of just being a simple adiabat in the convective region, you're adiabatic until you hit this region where convection is inhibited. And then you get a very steep temperature gradient, because now the only options you have to transport heat is radiation or conduction. Usually you find radiation is the more important one, but if you go to more massive planets and higher pressures, you can even get conduction. And in that case, it's actually hydrogen. It's not yet fully metallic, but it's sort of in this interesting transition region where it can start to contribute to the conduction. So because of that, now, right, so traditionally with these planets, if a planet cools, it will contract because you basically lower the inner temperature a little bit and it will evolve this way. But if you have this inner radiative region where the convection is inhibited, so as a planet cools with time, its radius, right, will not really shrink, because the first thing that will happen is it will just eat away at this very inner steep temperature gradient, and that will just shrink over time. So if you would plot the planet's radius as a function of time, right? So in the traditional picture, you just have this cooling and contraction curve, like Kelvin-Hamilton contraction. You can all do this like in your sleep over lunch. But instead, you find something that almost remains constant in radius. And this is while it's cooling, but it's just eating away at the inner region where convection is inhibited until that region is gone. And then you start evolving, you know, as you had done before at the same size. So here's the same thing, just plotted as the core temperature over time, right? So this is our standard evolution. And this is, so that you see the core is still decreasing in temperature, but it's just not reflected in the radius because you have to eat away this region first. So that's pretty interesting because, you know, we use planet sizes all the time to then infer what's on the inside, right? We use the planet size to infer how much hydrogen there should be, right? We also use planet size to calculate how much mass loss there should be as a function of age. And we can now measure, right? So when can you see this? This is like most important for planets that are young. So within the first 100 million years. And so we can start to test this observationally by looking at young planets. And this has been like a big push in the last sort of couple of years. The first results are coming out now. We're studying young sub-Neptunes. Partly for mass loss, we can actually see some of them losing their envelopes today. But one of the other interesting discoveries is they have pretty large radii, larger than naively maybe we should expect. And for one planet, it doesn't matter, right? One planet I can always find a radius time evolution and say, well, it just happened to live here. That's just what I'm found. But if you start to find loads of planets that are still very large given their age, we have estimates for their ages, then we have to see how easily you can explain it with the standard evolution model, right? Because you only spend a short amount of time at these large radii because you're cooling and contracting. So I'm not sure we can ever prove the existence of these inner regions where convection is inhibited for a single planet. You can show it's consistent, but you can't prove it. But I think if we have a sample, a collection of planets, where I think we should be able to distinguish an evolution where the radius is almost constant in size in the first 100 million years, versus a population where the radius decreases rather rapidly in the first 100 million years. And this will be an even stronger trend once you self-consistently account for the atmospheric loss that you expect for these planets, right? Especially if you want to explain a planet here now at 20 million years at this size, if it's just a standard thermal contraction, it has to have been like, in this case, 14 or 15 Earth radii when it was born. And you would have been losing mass much more rapidly then. And mass loss is also a way of cooling the planet and shrinking it. So this planet would have evolved even more rapidly to smaller sizes. So explaining this planet at 20 million years will be even harder. So there will be an even shorter amount of time. It's not impossible. You can always find a solution. But the question is, how much of a blink of an eye do you have to catch them, right, in this state? Hence the statistical argument. If you can look at none of them, I think we can distinguish these evolution scenarios. If, on the other hand, you're sort of doing this, your mass loss wouldn't have been larger early on because your size shouldn't have evolved in the same way. So this is one way I think we can statistically, observationally, just from the radii of young planets, learn something about their interiors. You know, is this really happening in their interior structure?
So how do they typically try to measure the age of these systems just from the star?
Yeah, it's from the stars. Yeah, some are much better than others, but I think there's like a very concerted effort now. Yeah, so initially people just looked at different stellar clusters, but there are now like a couple of field stars where people have developed supposedly data analysis to try to push this further. I think we will see. It's like a super active area. But I do think looking at the young planets is interesting for a variety of reasons. Yeah. Okay, so if there are no other questions, shall we talk about the super Earths a little bit? So in the very last, I don't know, 10, 15 minutes, depending on how much discussion time you want to have at the end. Let's talk about the consequences for the super Earths, right? So if the super Earths really were born as sub-Neptunes and then just evolved to be super Earths because they lost their hydrogen-helium envelope by hydrodynamic escape, then there should be some imprint of this history in their interiors. So one clear prediction is that all super Earths should be rocky, or all the cores of the sub-Neptunes have to be rocky because we can measure their sizes and further densities, and if they're causally connected, then this has to be what's going on the inside of these guys. Another thing, you know, if you need more convincing, if you look at the occurrence rate, so the numbers of sub-Neptunes versus super Earths as a function of time, several groups now have found that there are more super Earths around older stars compared to sub-Neptunes than around younger stars. So that really hints that the super Earths are born on sort of maybe a roughly a giga time scale in evolution. So that's intriguing. And very recently, sometimes we're lucky enough to also see, we can directly detect hydrogen escaping from these planets, typically using Lyman alpha observations, so the Hubble Space Telescope. Typically that's done for much larger planets like Jupiter's. But very recently, we're part of a group that found some evidence for escaping envelopes of some sub-Neptunes. So these are these smaller, so that would be the first, the smallest planets for which these detections have been made. So there's loads, I think, of lines of evidence pointing to this history. And as I said, you can model it really well. this is like a whole other talk, but it's most likely hydrodynamic escape, and then there's two different ways in which you can power it: photo evaporation and core-part mass loss. And I think Akash can tell you a lot more about this since he worked a lot on this with me. But the upshot is that in the past, we basically sort of independently sort of explained the observations. I think both models are a very good fit. But some recent work with James Owen, we've shown that most planets actually undergo mass loss in both of the regimes in their evolution. They usually start out on core-part mass loss and can end up as super Earths just doing that, but often transitioning into a photoevaporative regime. But these two mass loss mechanisms also mutually enhance each other because it's just a different sort of energy for powering the hydrodynamic escape. And planets should be able to both harvest the heat from formation as well as the photons from their whole star to drive the loss. So there's nothing that makes them mutually exclusive. But anyways,
How does hydrodynamic escape exactly work?
I will tell you that over lunch. Is that okay?
Okay.
Yeah. But it's basically a Parker type wind. And so it's just a hydrodynamic outflow from the envelope. And then you just have to ask yourself, where's the energy coming from? Yeah, but that's like a whole, let me tell you a little bit about the rocky planets instead.
Can collisions be important as well?
Collisions?
Yeah.
Yes. So can you ask me at the end? Because I thought about this a lot, and I actually think collisions could be really good at stripping the envelopes. And I think they may be too good. And I think you can turn it around and say, if there are too many collisions, and if they are really good at stripping the envelopes, you shouldn't have such a clean radius valley. Yeah. So I think the strongest argument in my mind for hydrodynamic escape is that you naturally get these slopes in these different parameter space, which is very hard to explain with collisions or other processes. Yeah, that's, but it's a very good, yeah. I'd love to talk more about collisions since it's bugging me. So how about the interiors? So for the super Earths, then, if they really were the interiors of the sub-Neptunes, the two things that you would expect is a lot of hydrogen and carbon, sorry, not carbon, oxygen, maybe carbon, but we didn't include this, hydrogen and oxygen in the metal or in the metal core, right? Because hydrogen and oxygen are both siderophiles, so iron loving. They would love to be in the cores. And if that's true, if that actually happens, then you should get underdense cores because, right, mean molecular weight of hydrogen is much lighter than iron, so that actually will reduce the density of the iron core significantly. So for 1% of hydrogen, you get a reduction in density of like 8% roughly. And so you may be able to see this in the mass radius diagram of the super Earths. So here is a plot that shows you as an example the different densities you would expect if you had allowed for planets having an iron core in which you were able to incorporate hydrogen and oxygen. So here's the Earth. We actually also slightly underdense. I'll come to that in a second. And this is sort of one of the solutions you can get if you account for the hydrogen and oxygen in the core. And it's a little bit intriguing because most of the planet mass measurements we have are not super good. So you can fit it with all the lines equally well. But the TRAPPIST system, we have, thanks to transit timing variations, amazingly good mass measurements. And they are, as the whole system is slightly underdense. So having bulk densities of 5 grams per centimeter cubed instead of 5.5. So this could be one explanation. Instead of appealing to larger amounts of water, which is a very common alternative solution. And then you can do a better version of that and do it for the whole exoplanet super Earth population, which was done here. And you can see that even for them, so again, for population, and if you renormalize this to Earth, you expect a density of 5 grams per centimeter cubed on average, instead of 5.5. And this is like the 1 sigma envelope and the 2 sigma envelope for the exoplanet population, accounting for the air bars. And I think there's tentative evidence that there is a population slightly underdense. So it could be because of their hydrogen-rich history. Okay, and last but not least, how about Earth? It's like you always get that at the end. What about Earth? So, right, when I studied planet formation, when I was a student, people would always say, well, for Earth, the presence of the primordial hydrogen disk wasn't important. Most of the assembly happened after the gas was gone. And so we can ignore hydrogen and all the disk interactions if you want to form terrestrial planets. That's the story I got. And maybe that's still true. But because we did all this work on the exoplanets, my colleague and collaborator Ed Young was like, well, I think we need to think about Earth again. So what clues are there about Earth formation? So one thing is we too have a core density deficit. Our iron core is not just iron. How do we know this? Because our density is lower than that of iron by roughly 10%. How do we know that? From basically seismic studies. So you basically see different velocities as that you transverse to the interior of the Earth. And so you can pretty well map out the density structure of the Earth. We don't know what is making the core underdense. There's many candidates. But already in 1977, Dave Stevenson, did a simple calculation saying, well, you only need 1% of hydrogen in the core, and that could explain all of the underdensity. The other evidence we have is that there is an imprint of the primordial nebula on Earth formation. It comes from these light or these noble gas ratios, right? So when you look at the abundances of, especially of neon 20 to neon 22, it suggests some nebula equation imprint. So some of our building blocks, you may remember at this stage. And we also can date actually the formation age of Mars using the Hafen tungsten system, and that comes out to be about 3 million years. And that's quite within the typical disk lifetimes that we see, and also the best estimates we have for our own solar system disk lifetime of the disk. So all this suggests that, so I don't want to claim that the Earth formed as a sub-Neptune and then lost its envelope, but I think the embryos. So what we looked at is, could the embryos that then are assembled by giant collision, giant impacts, could they have had an imprint in a history from having accreted in a gas disk? And is there any signature of that? So for that, the first thing to remind us of how big do you have to be to hold on to an envelope? So you just have to grow to size physically, or a mass that is large enough that your own radius is smaller, right, than the bonding radius. You can gravitationally hold on to the material. And for the solar system at 1 AU, that's roughly the size of Ceres. So that's okay, right? The embryos definitely, typically, we think Earth forms sort of from Mars-sized embryos in a giant impact phase, so that condition is satisfied. But the second condition, right, because we also want to have a magma-ocean interaction, so for the hydrogen to interact with the magma ocean and leave any imprint of that sort, you also need to do this while being hot enough, right? So the interior can be very hot, but if you make a small body too hot, the hydrogen will just become unbound again, right? So this gives you a more stringent condition. So you need to ask the question, can you accrete a hydrogen envelope, but can you also hold on to it at magma ocean temperatures? And that makes the requirement for the primordial embryos a little bigger. So you have to be sort of twice the mass of Mars at least. But if the embryos that formed in the disk that were later merged in the giant impact phase, if they are formed in the presence of the gas disk to sizes that were a bit bigger than, say, 20% of the current mass of the Earth, then you should have had conditions where the hydrogen and the magma ocean can actually chemically interact. So we looked at what this would lead to, and here are results for half Earth mass embryos. And so indeed, so this is the composition of the core that we find. So you get 0.5% of hydrogen and then almost 1% of oxygen and silicate. And so you can indeed, of course, then reproduce the density deficit for the Earth. So what you would need is about 0.2% hydrogen that was accreted in this embryo stage. So fine, it's nice that you can find a solution. What I think was even more intriguing to me is that, as I told you before, magma oceans and hydrogen make water. So the same model actually also gives you a couple of Earth oceans worth of water. So you would have a way to explain why Earth has the water budget it has. And instead of requiring just the right amount delivery, you get it sort of as a byproduct of this initial nebular phase. So this is right, the current Earth estimate. This is what's in the atmosphere, and that's in the silicates usually has less water. The water later condenses out as the planets go. So I thought that was intriguing. And then the last thing that you can ask is, because it's like a chemical model, you can ask what's the chemical state of the planet, right? And so what you find is that the oxygen fugacity, which basically is used to determine how oxidizing and reducing a planet or a body in the solar system is, like asteroids, is also well matched what you get from this chemical equilibrium model. So this is measured relative to the ion-Wüstheit buffer, and it agrees with the bulk Earth today very well. And it's very different from the initial building blocks that had this interaction. You know, the hydrogen gas is of course solar, and then the bulk Earth we modeled as encephalite chondrites because it matches best all the other bulk features of Earth. So no proof that this has happened. I think it's intriguing that it can explain these different observations with a single model. They all have been explained with different models in the past. So I find this slightly encouraging. But I think the best thing about all of that is that we don't have to speculate, that we will know the answer. We will at least know the answer whether hydrogen is responsible for the core density deficit of the Earth, because we can use neutrino oscillations. So people are already collecting the data for testing this. So if the Earth has 0.5% or 1% of hydrogen in the core, right, the neutrinos will change, the neutrinos will change flavor at different rates because the cross-section for neutrino oscillations depends on the proton to neutron mass. Hydrogen, of course, is unique compared to the other elements And so what you need is basically atmospheric neutrinos. So we're currently collecting the data. Basically, it takes 15 to 20 years to get enough cosmic rays that create atmospheric neutrinos that you get good enough statistics to figure out whether there is sort of half a percent to percent level of hydrogen in the interior of the Earth. So we can just wait and we'll find out the answer relatively soon. I was told like in 35, so I will still hopefully be alive then. So okay, with this, I think I'm actually more than out of my time. I'll just stop here. Thank you.
Thank you very much for an intriguing talk. We started a little late, so I had a question or two.
Are there any other uncertainties in the composition of the Earth that would change the luminosity by?
No, because you need the hydrogen, right? Because it's the proton to neutron ratio that you need. Hydrogen just, yeah, I mean, unless you can store a lot of hydrogen elsewhere. I think, yeah, I think this would be the dominant effect. Yes. Not an expert on this, but yes, that's from people we talked to and some papers I've been reading. And I guess people who are interested in the Earth have been doing these experiments for a long time and have been thinking about how could you infer what's in the interior. Yeah, the debate of what's making Earth core underdense is a long one, right? Carbon is another candidate that could be responsible. You just need a lot more carbon by mass to get the same density deficit because it's mean molecular weight is not that different. Yes.
And I think the standard picture for Venus's different atmosphere is that it lost its hydrogen from evaporation.
Yes, that's right.
So when you do the exoplanet wind models, do you then also have to worry about chemical fractionation or escape of different species? And does that affect the long-term chemical evolution?
Yeah.
Or is it just the atmosphere?
No, that's a great question. So that's actually something we're working on right now. So there are several things. I think in some of the observations of direct escape, people are looking now also for oxygen and other species, so you can see that. Initially, we find that the hydrodynamic escape is so fast that you actually don't fractionate. However, later in the evolution, you should be able to get mass-dependent fractionation. So there have been papers already suggesting that you may get enhancement in helium as a result. I think we need to do slightly more careful modeling also with the ionization structure, because it depends critically on exactly from where in the envelope you drive the mass loss, on how much fractionation you get. So it's like a slightly complicated problem, but it's definitely, yeah, it's definitely on our radar, and I think it will definitely happen. And we know already if you transition from a sub-Neptune to a super Earth, so if you lose so much of the envelope to really sort of, you know, basically almost everything, your envelopes for sure will become water dominated at the very least. Both because you lost so much hydrogen, but also because if the chemical interactions, the chemical equilibrium is ongoing, you start to produce water dominated envelopes at the same time. Yeah. Yeah, so it's like a very rich, this is a very good, and that's something else I think observationally we should be able to probe, either through the scale mean molecular weights and scale heights, or just directly by observing some of those other species in outflows.
So let's thank our speaker again and continue some of this solar launch.